right, so we're going to look at 3 different sampling distributions. And as we're doing this, instead of working through the entire sampling distribution and table like we did a couple of examples ago, what we're going to do is we're just going to talk about this in general. So technology has been used to generate these results, and we just kind of want to talk a little bit about what that's going to mean. So in each of our simulations, we're going to do 3 of them. Our P is going to be 0.25. So 25% of the entire population are going to be cat people in each of these different simulations. All right. So before we get started, we'll answer a couple of questions. Will each sample contain 25% cat people? No. Right? Each population total is 25%, but our samples and our statistics will vary. So we'll say no, our sample statistics will vary. Right. Is it possible to get a sample with 0 cat people? Yes, it is possible. All right. As we saw, again, in our previous example that we worked through. Okay, so in simulation 1, we are starting with a population of 8 people. We are starting with a population of 8 people, so we have a relatively small population, 2 of whom are cat people and 6 of whom are dog people, so there's our 25%. Right, random samples of 4 are taken from this population, and the percentage of cat people are noted for each sample. Our mean of our sampling distribution is 25%, and our standard error is going to be 16.4%. Right? So when calculated, the mean of our sampling distribution is 25%. The same value of P. This indicates that our estimator P hat is unbiased because 0.25 minus 0.25 gives us 0. So the fact that this mean here is the same as our population means this is unbiased. Our standard error is 16.4%. Because, and we're going to kind of compare our standard error as we go through the next few simulations. This is going to be the largest one that we see because we have the smallest population and sample size. All right, for simulation 2, this time we're comparing or considering a population of 1,000 people, 250 of whom are cat people. So our population proportion is 25%. We're going to take random samples of size 10 using technology, and then if we go through and we look at this, our mean is still 25%, so we are still unbiased. Notice that our standard error has gotten a little bit smaller. Our standard error is now 13.6% instead of 16.4%. Right. Now if we increase our sample size by quite a bit, we're looking at a population of 100, a sample size of 100. We're still going to have a 25% for our population proportion. Our mean of our sampling distribution is still going to be 25%, but notice that our standard error drops a lot to 4.2%. Okay. So what we're going to think about as we're comparing these is what happened to these means and what happened to these standard errors. Okay. So if we go through and we summarize kind of those 3 different little paragraphs that we just looked at, our first one, we had a population size, so a capital N of 8, a sample size of 4, a population, a P value of 0.25, a P hat, right? Our mean of our sampling distribution was 0.25. Our bias, well, we take our difference, 0.25 minus 0.25 gave us 0, so we said that was unbiased. Our standard error we were given was 16.4%. In our second simulation, we had a larger population, sample size a little bit larger. Our mean of our sampling distribution was 0.25, so again, this was an unbiased result. Our standard error in this case was 13.6%. And then in our last little paragraph there, we were told that we had a larger population, but we also took a much larger sample. Our mean was still 25%, so all three of these were unbiased. And this time our standard error shrunk considerably to 4.2%. So again, kind of just looking at the notation here, just as a reminder, this capital N was our population. That way, if you want to go back and look at these, our lowercase n is our sample. P is our population proportion. Right? P hat is our proportion, right, of our samples. Right. Our bias, again, we found the difference between those two values. And then standard error, we're going to eventually get a formula to calculate. All right, so as a summary, right, the estimator p hat is unbiased for all sample sizes. Right, so all of these rows where we calculated our bias, we got 0. Right, this is always going to be true as long as we take random samples. Right, and that's because our difference turns out to be 0 because the mean of the estimator, our p hat, right, was equal to our value for our parameter. Our means and our parameters were all 25%. They were all equal. Right, the precision improves as the sample size gets larger. That is because the standard error gets smaller as the sample size gets larger. Right, again, standard error, when we're thinking about precision, we're thinking about standard error, standard deviation is spread. So there is less spread when our sample size gets larger. Right? The shape of the sampling distribution is more symmetric for larger sample sizes. We can see this by comparing histograms on page 10. In simulation 3, where we have our largest sample size, we had a more symmetric looking distribution. All right, so all of this, if you remember nothing else from these examples and these comparisons of these simulations, the actual details for each one is not really what we're looking for here. What we're looking for is what we're seeing in this summary. Right? It's unbiased, our precision improves as our sample size gets larger, and the shape of our sampling distribution is more symmetric for larger sample sizes. So we're going to take the last pretty much 3 pages of our notes and all condense them into one sentence. So if you don't remember anything else, don't worry about anything else. What you want to pay attention to is this very last sentence that we're going to write here for our conclusion. So we are going to say, the larger the sample size, the more precise and normal the sampling distribution. So the larger the sample size, the more precise and normal the sampling distribution. Right, so again, don't worry too much about those individual simulations and all the different numbers that are in there. We just want to look at the summary. Right? The larger the sample size, the more precise and normal the sampling distribution, because this is something that is going to keep coming up in problems as we move through the next few sections.